Alright, so this is the June 2010 Unit 2 paper on the mechanics, waves and interference. So let's have a look at this first question, which is going to be about moments. So let's just zoom out a little bit so we can see all of it. So we've got a motorcycle rider and it's in contact with the rotor A and B. So just to sketch it, therefore there are going to be reaction forces at these 2 points because that's where it's in contact with the ground. Okay, so the motorcycle has a weight of 1100 newtons and the rider's weight is 780 newtons. State the principle of moment. So essentially what this means is that the sum of all of the moments is equal to 0, or in more general terms, essentially the sum of the clockwise moments equals the sum of the anti-clockwise moments. Alright, so that's what we've got here, a statement to be in equilibrium, clockwise moments equals the anti-clockwise moments. Okay, so let's continue on. Calculate the moment of the rider's weight about B. So we've got a perpendicular distance of 0.35 and a weight of 780. So moment is force times the perpendicular distance from the force to the point. So it's 780 times by 0.35, which gives us a value of 2.7 times 10 to the 2 newtons to the right number of significant figures. That's a 3, by the way. All right, so that's that one. So let's move on to the next question. By taking moments about B, calculate the vertical force that the road exerts on the front tyre at A. So let's draw a simplified diagram. So this is where B is. There's the weight force of the rider. There's the weight force of the bike, and there was the reaction force there, and it's that reaction force we're trying to calculate. So we know essentially what the length is. So we know that R is 1.3 meters from B. So that is the moment going around. You can see is the moment going around clockwise. So the moment's anti-clockwise. So we can see these ones are rotating around this way. It's going to be the one we did last time. So the moment of the weight force, 780. And then we also need the moment of the weight of the motorbike itself, 0.6. And then, so that's going to give us a value of the reaction force to 2 significant figures of 7.2 times 10 to the 2 newtons there, to 2 significant figures. Okay, so calculate the vertical force at B. So we're going to apply the linear equilibrium condition here. So upward force is going to equal downward force. So we know that the 2 normal contact forces must be equal to the 2 weight forces. So the normal contact force we don't know, I'm going to call it R2, would be the sum of the weight forces. So 780 plus 1100 minus, I think it was like 717.5, and putting all those 2 together gives us an answer of 1200, or 1.2 times 10 to the 3 newtons there. Maximum power of the motorcycle is 7.5 kilowatts and a maximum speed of 26 meters per second when it's traveling on a level road. Calculate the total resistive force at this speed. So at maximum speed, acceleration is 0, which means at maximum speed, the forward force from the engine is equal to the resistive force. So let's work out what the thrust force of the engine is at top speed, because that would be equal to the resistive force. So power is 7,500, velocity is 26, and so we put those two things together, we end up with 288.46, or 2.9 times 10 to the 2 newtons. That equation calculates the forward force of the engine at that given velocity, but if it's at maximum speed, that means resultant force is 0 because the acceleration is 0, so that must be equal to the frictional force. Okay, so that completes question 1. Let's move on to question 2. Okay, so Galileo used an inclined plane similar to the one shown in figure 2 to investigate the motion of falling objects. Explain why using an inclined plane rather than free fall would produce data which is valid when investigating the motion of a falling object. So as part of your course, you should have done an experiment where you measure g by free fall, and what you'll identify is one of the problems you have is the impact of timing errors because the times are so short. So that's the problem with free fall, is the incredibly short time, and this is a way of essentially making the time longer. And also, as the object is traveling slower, then there's going to be a smaller impact of air resistance as well. So this is quite useful, those things. So let's put that into words. Alrighty, so that's what we've got there. I've just put down what I was talking about and contextualize it in terms of the uncertainty. The other thing you have to realize is Galileo didn't have stopwatches, so his timing measurements would be more crude, so anything he could do to make the time last longer is a good thing. Okay, so we've got a demo of the setup. The number of swings of a pendulum was used to time a trolley after it was released from rest. A block was positioned to mark the distance that the trolley had travelled after a chosen whole number of swings. Okay. So the mass of the trolley is 0.2 kilograms and the slope is an angle of 1.8 degrees to the horizontal. Show that the component of weight force acting along the slope or parallel to the slope is 0.06 newtons. So the component parallel to the slope is mg sine theta. So that's 0.20 times by 9.81 times by sine of 1.8. You might want to verify your calculator is in degrees at that point, as that's what typically leads to an error here. And when you do this, you end up with 0.0616 which is approximately 0.06 newtons. So that's worked out fine. All right, let's continue on. So now we want to calculate the initial acceleration. So acceleration is force divided by resultant force divided by mass. So mg sine theta over m. So we actually see it's g sine theta. So 9.81 times by sine 1.8. And we calculate that. We get a value of 0.31 meters per second squared. Two significant figures. It's actually 0.308 blah 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 blah, but two sig figures is appropriate here. In this experiment, the following data was obtained. A graph of the data is shown below it. So one pendulum swing gives that distance, two gives that distance, blah blah blah, and we've got what looks suspiciously like a quadratic relationship here. Okay. From the graph, state what you would conclude about the motion of the trolley. So effectively what we had is a distance versus time. We had a different unit of time because we had time in pendulum swings, but it's still distance versus time. And the gradient of a distance versus time graph is velocity. And the gradient was increasing, therefore we know the speed or the velocity was increasing, so it was accelerating. And that's what we can do to it. So let's put that into words. Alright, so that's what we've got there. Increasing gradient, increasing speed, accelerating. Alright, so if each complete pendulum swing has a period of 1.4 seconds, use the graph to find the speed after it has travelled 3 meters. So first of all, I'm going to find the time at which it gets to 3 meters. So reading off the graph, the time after 3 meters was 3.15 pendulum swings, so that's 4.41 seconds. So that's the time. So let's get the rest of the Subat stuff. Okay, so we know the displacement is 3 meters. The initial velocity is going to be 0 because you let it swing from stationary. We don't know what the acceleration is, but we do know what the time is. Okay, so what we're going to want is an equation without a in it. So that's going to be u plus v over 2 times by t. We can get rid of u because we know it's 0. So we know the velocity is 2 times the displacement divided by the time. So that's 6 over 4.41, giving us a value of 1.4 meters per second to 2 significant figures there. Incidentally, we could have also done this by drawing a tangent to the graph at the right point and determining its gradient. That would have worked as well and been a very effective method for doing this, but this is the method because I find it's quicker to do it this way. Okay, so that finishes that question there. Let's move on to the next. Alright, so this question we're going to look at some waves. So the first thing we want is the amplitude of a wave. That's the maximum displacement from the equilibrium position. Alright, so let's move on quickly. Other than electromagnetic radiation, give one example of a wave that is transverse. That's fairly straightforward. You go with water waves are an example of a wave that is transverse. You can make transverse on a rope or I don't know, some kind of slinky, but like water waves are the classic example that we usually go for here. Okay, state one difference between a transverse wave and a longitudinal wave. So it's the direction of the particles of the medium is different. So in a transverse, the particles of the medium oscillate perpendicular to the wave motion. In a longitudinal, they're parallel to the wave motion. We could also go with transverse can be polarized, longitudinal cannot. So let's go with those. Alright, so we'd only need one of those two to get the 1 mark, so I would go for the second one because it's quicker to write, going about polarization. But anyway, let's move on. So we've got 2 identical polarizing filters A and B, and an unpolarized light to start with. The arrow indicates the plane in which the electric field of the wave oscillates. The polarized light is reaching the observer. Draw the direction of the transmission axis on filter B. So essentially, what it should be is essentially it needs to be in the same direction. So it needs to be a vertical line in order for the polarized light to go through. So let's see if we can draw that. It's a bit wonky, but you get the idea. It's in that direction there. All right, so that completes that one. So the polarizing filter is rotated clockwise through 360 about line XY. On the axis below, sketch how the light intensity reaching this area varies when it's done. So at 0 degrees, it's going to be a maximum because it's inside the plane of polarization. So it's going to be here. At 90 degrees, you're going to get nothing. And it's going to vary between maximum, nothing, maximum, and finally maximum at the end. So it's going to be some sort of a sinusoidal kind of shape. This is going to be really wonky, but okay, so draw it smoother than that. That's really wonky, but I'm afraid that's the best I can do on my screen. So state one application other than education of polarizing filter and give a reason for its use. So these are used any time light is reflected. So if you're snowboarding, skiing, or if you're on water, you're going to want these because it will essentially filter out any reflected light which has become polarized, which is really useful and protect your eyes from excessive glare. So let's get that. Alrighty, so that's what we've got there, and by filtering out glare, essentially all that leaves them is with just the normal light you would get if you didn't have reflected light, which is kind of what you're going for. So that's an application of a polarizing filter. They're also used in 3D glasses, not so much now, to be honest. They've got a bit beyond that tech, but they certainly used to be used in 3D glasses, and you have one on your computer screen. That's used as well. So there's a few different uses, but that's the one I would go for. So that finishes off question 3. Let's move on to question 4. All right, so we've got a gymnast trampolining. Right, and we're using springs on the trampoline. Okay, in traveling from her lowest position at A to her highest position at B, her center of mass rises 4.2 meters vertically. Her mass is 55 kilograms. Calculate her increase in gravitational potential energy. So change in gravitational potential energy is mg delta h. So it's 55 times 9.81 times by 4.2. Looks a bit rough and ready, but whatever. Gets the job done. And when we do that, we end up with 2266. So essentially, it's going to be 2.3 times 10 to the 3 joules to 2 sig figs, which is appropriate here. Okay, so that's going to use that one. Let's carry on. The gymnast descends from her position B and regains contact with the trampoline when it's in its unstretched position. At this position, her center of mass is 3.2 meters below its position at B. Calculate her kinetic energy. So essentially what we've got to start with, she's stationary at the top, so she has GPE, nothing else. When she reaches B, we're going to use that as our 0 line, so we're going to say she's transferred all the GPE into kinetic energy. So that means her kinetic energy is going to be her GPE with reference to the 0 line, which we're using at position, which she is now 3.2 below B. So it's going to be 55 times 9.81 times by 3.2 there. And if we do that, we end up with 1724. So essentially 1.7 times 10 to the 3. If you don't want to use her current position as the 0 line, because maybe you don't like that method, if you use the bottom position as a 0 line, she would still have some GP at this point. So you can calculate her original GP, her final, and the difference between those is kinetic energy. So if that's your preferred method, go for it. I always try and pick 0 GP line in the most convenient place possible. So in this, I picked at the location she finishes. Calculate her speed. So kinetic energy is half mv squared. So the velocity is going to be 2 times the kinetic energy divided by mass, all square rooted. So it's 2 times by, I think it was 1 724.8 divided by 55 square rooted, and that gives us a value of 7.9 meters per second. Theoretically, you could also have solved this using SUBAT if you wanted to, but I'm not sure why you would do that, but you can do if you want. Draw an arrow on figure A to show the force exerted on the gymnast by the trampoline when she is in position A. So I can't get the diagram back up, unfortunately, with this, but essentially there'd be a force acting upwards at her feet that's going to accelerate her upwards. As she accelerates upwards again from position A, she's in contact with the trampoline for a further 0.26 seconds. Calculate the average acceleration she would experience while she was in contact with the trampoline if she is to reach the same height as before. So to reach the same height when she leaves the trampoline, she needs to be going at 7.9 meters per second. Okay, at A, she's going at 0. She's stationary. So essentially, she needs to experience a change in velocity of 7.9 meters per second. Acceleration, or average acceleration, is dv by dt. So 7.9 divided by 0.26, which is roughly timesing it by 4. So we're expecting an answer around 30, and indeed we get 30.46. So let's give that to 30 meters per second to two significant figures. Okay. So that finishes off that one. Let's continue on with question 4. Alright, so on her next jump, the gymnast decides to reach a height above position B. Describe and explain in terms of energy and work the transformations that occur as she ascends from her lowest position A until she reaches her new position above B. Okay, so let's think about the energy exchange we've got going on. So to start with, she's going to have stored elastic potential energy. That's because we've stretched out the springs. That's the form of the energy. As she ascends, that's going to be turned into kinetic energy when the trampoline becomes unstretched. And then finally, it's going to be to GP when she reaches her maximum height. So if she wants to get above B, she's going to need to put in some work. And she'll do that with her legs by jumping. And you're going to need that for two reasons. One, she's going to be transferring energy against air resistance and forces. So those would act to make her reach a height below B. And to get above B, she also needs to do some extra work to increase her total energy as well. So that's the general idea. Let's put that down into text. Right, so let's start off with this. We're just describing the energy exchanges from elastic potential energy to kinetic energy, GP, and some work done against air resistance. And then finally, when she reaches maximum height, all of the energy is in the form of gravitational potential energy, and some has been lost to the surroundings as work done. All right, so that's our starting point. So let's look at how she can get to a point above the height. So if she's going to reach the same height, she's going to need to do some work by applying force with her legs, because she needs to put in the energy she's losing against air resistance. If she wants to go higher, she has to do even more work, because that means she needs to increase her total energy. So let's put that into text as well. Alright, so let's review what I've got here. So to reach the same height, just do some work to compensate for the energy she lost to the surrounds. Let's try that again. Surroundings. And if she wants to reach an even larger height, she must do even more work because she wants to increase her final GP. So she must start with more energy because energy has to be conserved. All right. So that's essentially how that works, and that would be my answer to this question. All right, so that finishes question 4. Let's move on. Okay, so we've got a rubber cord is used to provide mechanical resistance for fitness exercises. You may have come across a few of these. So it's going to be stretched by applying a force and looking at how the extension changes with force. Okay, so we've got a loading curve, curve A, and an unloading curve B. State which feature of this graph confirms that the rubber cord is elastic. It's the fact that the final extension is 0, so there's no permanent extension. Alright, so that's that one. Explaining your method, use the graph to estimate the work done in producing an extension of 0.30 meters. So that's here, so 0.3 is this point here. Whoa! Alright, so we want to know what the area is underneath the graph A. So let's count the big squares first. So 1, 2, 3, 4, 5. Yeah, basically that one. 6, 7, 8, 9, 10. Between this one and this one, that makes 11. And then between the other ones, I reckon that's another square there, so 12. And then I would put those together to make an 1.5. So we've got 12.5 big squares, and each square is 10 times 0.5. So let's start explaining what we're doing. So the first thing is to explain what we're doing. To get work done, that's the area under force versus distance, or extension in this case, graph. So let's then show what we were doing just now. Okay, so then each big square is 0.05 times 10, so about 0.5 joules. I counted earlier, there's about 12.5 big squares. That's 6.25 or 6.3 joules to 2 significant figures, which would be appropriate for this question. There'll be a range of different answers, probably something between like 6 and 7 at a guess for this, to allow for the fact you count the squares slightly differently. All right, so let's continue on. Alright, so we've got a linear graph up to an extension of 0.04 meters. Calculate the Young modulus of the rubber for small strain. So we've got an area, we've got original length. So first thing we need to do is pick up what the force was at 0.04. So let's go back and get that. That's a force of 10 newtons. 10 newtons, and your extension is 0.04. Careful not to do what I did quickly the first time, is read that as 0.4, not 0.04, which would give you 50 instead, which is not right. So Young modulus is FL over A times extension. So we've got 10 times by 0.5, that actually looks like 1.0, that's definitely 10, divided by 5 times 10 to the minus 6, that's your area, times by 0, that looks like divide, times by 0.04, where we put those values together, gives you 2.5 times 10 to the 7 pascals, or newtons per meter squared. Okay, so a scientist compared this cord with a steel spring that reached the same extension for the same maximum load without exceeding its limit of proportionality. Draw the load extension line for this spring up to a load of 50 newtons and label it C. So essentially what you should have drawn on there is a straight line through the origin, but finishing at the same place. I can't flip back and then draw that and show you because of the program I'm using, but let's just note that so you know what we're doing. Alrighty. So, with reference to the spring, explain what is meant by the limit of proportionality. It's the point at which the force versus extension graph is no longer linear. I probably shouldn't use the word linear in that it is no longer a straight line graph, or the force is no longer directly proportional to the extension. So let's get those. Alright, so that's what we have there. So that finishes off this question. Let's go on to the next one. Okay, so for a plane transmission diffraction grating, we've got the equation for first order beam is this, because n equals 1, so it's why it's not n lambda, it's just 1 lambda. So we've got 2 of the slits in the grating, we've got a distance d, so d is this slit separation, so if we draw that on there, essentially that's d, and if it's a first order wavefront, that on there is the wavelength. Okay, so that's that one, and with d I'm trying to show the distance between those two blobs that were the centers of the adjacent slits there. Okay, so state and explain what happens to the value of theta for the first order beam if the wavelength of the monochromatic light decreases. So we look back at our equation. So lambda is d sine theta, and d has remained constant, so we can see that sine theta and lambda are directly proportional. So if we decrease the wavelength, we're going to decrease sine theta, and that means we're going to decrease the angle as well, as theta and sine theta always do the same thing. Alright, so that's what we've got there. So if we move on to the next question. Okay, so a diffraction grating is used as part of a spectrometer when we look at the wavelengths from distant stars, and we get a spectrum X. And we've got the line spectra for different elements. Place ticks in the box of the 3 elements that are present. Okay, so if you look at Mercury, we can see there is a line for every single line of Mercury. So Mercury is definitely present there. If we look at strontium, the lines match up here and here, but you can see here the lines do not match up there, so it's not strontium. Calcium, likewise, we can see don't match up along here, so you need complete matches. Sodium, it looks like it matches up, though it's a little bit hard to tell. They look a little bit closer together on sodium, but I'm going to say that one is, but we'll come back and check. Helium, looks like we've got all the lines matching up, so that one looks a dead cert. Okay, and then if we look at hydrogen, we're looking at a star, you'd expect it to contain hydrogen, and yep, looks like it does. So let's go with hydrogen being present as well. So it turned out that actually the strontium wasn't right, these two were closer together than those ones, so it's not sodium. The diffraction grating used to attain the spectrum of a star has 300 slits per millimeter. Calculate the distance between the centers of 2 adjacent slits on this grating. So D is 1 over n when n's in meters. So if there are 300 slits in a millimeter, there are going to be 300,000 in 1 meter. So then when we calculate this, we end up with 3.3 times 10 to the -6, or 3.3 micrometers. Calculate the first order angle of diffraction for line P. The P looks like it's 545, I would say, nanometers. So we'll be using a diffraction grating, so n lambda is d sine theta. It wants the angle, so and n is 1 because we're looking at the first order, so theta sine to the minus 1. The wavelength, which I said I reckon is 545 times 10 to the minus 9. And you're going to divide that by d, which we've just got. It's 3.3 times 10 to the minus 6. And when we calculate that value, we get a value of 9.4 degrees. That'll be a range of answers because you were guessing what the wavelength was, but it'll be somewhere around that if you've done it correctly. All right, so let's move on to question 7. Okay, so a glass cube is held in contact with a liquid and a light ray is directed at a vertical face of the cube. The angle of incidence at the vertical face is then decreased to 42 degrees. Okay, so then at this point, the angle of refraction is 27 degrees, and you've got tau TIR happening at P. Okay, so first thing I want to do is complete the diagram. So we've got total internal reflection. So we're going to get a line going here where the angle of incidence and reflection are roughly similar. It's going from glass to air, so that's decreasing in refractive index, so we should see it bend away from the normal there. That's what you'd be looking for on that side of your diagram. So the things you'd be looking for, this angle in here and this angle in here should be pretty much the same. This angle in here, the angle of incidence, should be much smaller than the angle of refraction. It's going to bend away from the normal. Okay, so let's go carry on. So show that the refractive index of glass is about 1.5. So glass is the second. So using Snell's law, N1 sine theta I is N2 sine theta R. So it's going from glass, so this one here is just 1. So N2, the sine of the angle of incidence, the sine of the angle of the refraction. So we've got sine 42 over sine 27, so that's going to give us 1.56 blah blah. So no, it's not. It's 1.474. So giving us 1.5 to the two significant figures. So that seems right. It's actually, let's write out the unrounded so we can show we've actually done the calculation. So 1.474 yada yada yada, which is roughly 1.5. Okay. Calculate the critical angle for the glass liquid boundary. So do we know anything about the liquid? No, we don't. Okay. So it's not done by that method, it's just actually looking at what the angle of incidence is, because if it's totally internally reflecting, we're going to guess that's the, because it says it for the first time, so it's going to be 90 minus 27, which is 63 degrees there. So if I show you on the diagram what I'm doing, essentially if that's the normal, I'm trying to work out what that angle is in there, if that one is 90 degrees, so that's 63. Nice question there, love it. And then finally, calculate the refractive index of the liquid. Okay, so If it's totally internally reflected, that means that the sine of the angle of refraction is 1. So we can do n1 sine theta IC is just equal to n2. So that's just going to be 1.474 times by sine 63. And if we do that, we get like 1.3 blah, 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 which is 1 point. This is not going well. Come on. Okay, which is 1.3, which is what you'd expect because you know it needs to go from high to low to get totally internally reflected. So you'd expect it to be less than 1.5. So that's good that that is. Okay, so that completes this paper. I hope you found that useful. If there are any issues with this, please do comment and let me know. If you found this useful, do check out my other playlists which have Unit 1, 4 and 5, as well as these Unit 2 ones I'm making. But thank you for taking the time to come and watch through this. I hope you found that helpful.